Okay, so I didn't really know what to erase. I wanted to leave the numbers up and I wanted to explain what's going on here, so I have to do the best I can. So the critical thing of why we're using 2 to the 2 to the n minus 1 comes into how this factors. So what is the rule when I have a to the b to the c? What's our rule with powers?
Well, this is a to the b times c.
A to the b times c. So we have our base, and then we have the two powers, b and c. Okay. So we have, in the example we're using here, we have 2 to the 2 to the n. That's going to be x. Two to the 2 to the n. What does x squared equal?
It's 2 to the 2 to the n squared.
2 to the 2 to the n squared. So what are my powers here that correspond to like my tower here?
Well, that correspond to b and c.
Yeah.
Well, you have 2, n, and 2.
All right, which one's b?
So b is the bottom power, so that would be 2. This,
Okay. Which one's c?
I guess, n could be c.
Okay.
And then you have to have an extra one.
All right. What if I wanted to write something as b and something as
Well,
c here?
then we would say 2 to the 2 to the 2n. Because we can multiply these two.
Well, okay. So we got a little bit of confusion here. I want to have something like a to the b to the c here, and I have 2 to the 2 to the n squared. So what's a? Let's start there.
A is 2.
A is
bottom
2.
2.
What's c?
C is this top 2.
What does b have to be?
Then b would have to be 2 to the n.
2 to the n. There we go. And you see the three? See the three things?
Yep.
All right. 2 to the 2 to the n squared. So what does this equal? What does 2 to the 2 to the n squared equal?
Well, it equals 2 to the 4n. Because the powers all multiply together.
Okay, and what are the powers?
2 and 2 to the n.
2 and 2 to the n. What do you get when you multiply 2 and 2 to the n?
Well, then you get 2 to the n plus 1.
So I just say 2 times 2 to the n. And, right, so I get 2 to the 2 to the n plus 1.
Alright.
All right, so that's tricky. That is tricky to see. That's x squared. What's x to the 4th? Gonna be
Well, we sort of the same thing.
2 to the 2 to the n to the 4th.
Yeah. And then c is 4 here.
Right. So I get 2 to the 4 times 2 to the n.
So it's
Which
2
is 2 to the 2 to the n.
n plus, it would be n plus 4. No, it would be n plus 2.
2 to the 2 to the n plus 2.
Want to receive?
Clever. Clever. So now, x to the 4th plus x squared plus 1 factors into this. Okay. So when x is, I guess I'm going to have to erase, unfortunately. When x is 2 to the 2 to the n, I get this side equals 2 to the 2 to the n plus 1 minus 2 to the 2 to the n plus 1 times 2 to the 2 to the n plus 1 plus 2 to the 2 to the n plus 1.
Okay.
Okay. So an interesting thing happens. This number, which is 2 to the 2 to the n plus 2, that's what we said x to the 4th was, plus 2 to the 2 to the n plus 1, See this, how it goes n plus 2, n plus 1, and then a 1?
Yeah.
This one goes n plus 1, n, and then a 1.
Hmm.
So when I'm going up my towers of n, alright, I keep crashing into our radiator here. N equals 0 is where I start, and I got 7. When n equals 1, we got 3 times 7.
Yeah.
It's because this number that we're looking at here has the same form as this number. It's just this one's going n plus 1, n, 1. This one's going n plus 2, n plus 1, 1. So this is the prior number. That's the prior number. That's the one up in the list. 2 we got, was it 13 times 21? And this was the prior number up in the list.
Yeah.
See that? For 3 we got 241 times
Whatever that was.
whatever this was, the prior number up on the list. So we keep looking backwards. This clever factoring trick, because x squared plus x plus 1 is the same kind of number as x to the 4th plus x squared plus 1. What's the only difference between those two?
You just have an extra 1 in these two powers.
Yeah, so that creates the x to the 4th, x squared, x. They're similar. And that allows us to always look backwards and find exactly the prior number in our new number. But they don't have any common factors. The new number you introduce has no common factors, so you pick up more primes along the way. And you can put this into a computer, and as we saw on the Internet Sequence Database, we saw how the numbers get super big, super fast.
Yeah.
But I don't know if the number of primes gets super big, super fast, but just the numbers do. All right, that is very cool. That's a hard proof. Definitely hard. But it's neat. It uses a lot of algebra, and it uses a lot of number theory. Very cool. Do you understand it, do you think?
Yeah.
Sort of?
Yeah. Kinda, sorta.
I'd never seen this before yesterday, so anyway, that was fun. Good work this morning. Good work.